I'm making this video specifically for early stage researchers who are thinking of going on a short-term scientific mission to a large-scale user facility. I'm going to Nijmegen to visit HFML FELIX laboratory. And although there will be a lot about one experiment here, I'm not focused on that. No, my purpose is to show you the difference in working here compared to a normal university lab. And I'll try to capture that through the experience of one ESR on a short-term scientific mission here.
My name is Fatima Baterdouk. I'm a PhD student in Université Paul Sabatier Toulouse. Now it's Université de Toulouse.
This is the workstation where she will make use of the high-intensity infrared beam that comes down this silver pipe.
So actually what we are trying to do in the experiment is to measure the infrared spectra of polycyclic aromatic hydrocarbon molecules. The infrared spectra has not been done yet experimentally. This experiment is important to be able to get these fingerprints of these specific molecules and compare it to the infrared that emission that we observe in space in order to identify the type of molecules that could exist there.
Right here we're in the heart of the free electron laser. This is where the accelerators are, where we accelerate the electrons and then extract energy from them in the form of light. We are free electron lasers, so electrons enter the accelerator, which is the big blue tube over there. That's the first accelerator. And then over here we have the second accelerator. And then we select which undulator they have to end up in. The undulators are an array of magnets with alternating magnetic field. So the electron bunches will go through them in a wiggling motion. When they change direction, they have the tendency to release energy in the form of electromagnetic radiation. That's the principle of our FEL. The radiation is captured between two mirrors. The small portion of the light is coupled out through a small hole in the mirror and distributed through our building to the user station that's actually doing the measurements.
The waiting list of scientists asking to use this equipment is long. It is totally oversubscribed. In your proposal to come here, you have to say how much beam time you will expect to need.
We asked for 6 shifts and we get 4 based on the availability and the schedule that they have.
And a shift is what? An allocation of?
For us, we got like 4 night shifts from 5 to 12:30 after midnight.
Unlike in perhaps many scientific academic departments in the university, there are more constraints here, and therefore you expect the students to have a different experience of science.
Yeah, what I usually see, and I had the same experience when I really started here, we were users before also, it's really that there is a very strong constraint on the time, in the sense that we have a fixed schedule where we can use the laser. So the FELIX infrared laser, that's the main tool. Our instrument is coupled to it. And this was planned 10 months before, that exactly on this day at, let's say, 5 p.m. the light is with us. So that means that at that point we have to be ready. So we have to, everything from our side, as the user station or on the beam line, we want to say it, we need to be ready when the light comes with the project we want to do. And that is something that in a normal lab you might not have, because if something breaks, for example, just before, you can maybe say, oh, I'm tired today and I need to think about it, so I come back tomorrow morning and fix it then.
The experiment is quite difficult. It requires a lot of know-how to get all the steps to work.
What will happen is that this molecule will be tagged into what we call messenger that cannot react with the molecule that we want to study, but it will just stick to it as a tag. And in this case, when you shine the light in these tagged molecules for a certain energy, you will be able to untag the atom And at the same time, you will be able to get the infrared spectra of this molecule.
In a nutshell, it works like this. Admit the hydroxypyrene molecules into the vacuum chamber and ionize them. The molecular weight is 218. Add the messenger tags, water. Their atomic weight is 18. They stick to the hydroxypyrene. The tag molecules now weigh 236. Count these tag molecules with a mass spectrometer. Then select a particular frequency for the FELIX laser to generate. Irradiate with this infrared beam for 2 to 4 seconds. Count the number of tag molecules still remaining. If this number has gone down, tags have been shaken off because the molecule resonated, which means this particular infrared frequency is a vibration frequency of the hydroxypyrene. If the number with tags has not gone down, it shows the molecules have not resonated. So this infrared frequency is not a vibration frequency of the hydroxypyrene. By stepping through the frequencies of this infrared beam and repeating this procedure, the whole spectrum is plotted.
Or always going down because it
Emptying and refilling the chamber can take 7 seconds. So plotting a whole spectrum like this takes hours.
To be more specific, it's...
The FELIX lab allocated a week's preparation time at her workstation to get the experiments ready for the beam.
For Fatima's project, we started a week before with really preparations here. We had a lot of ideas, some of them did not work.
For this workup period, Christine Joplin, Fatima's second supervisor, was here, along with Alex Marciniak, who is her main supervisor.
During this time, we worked like 12 hours per day to just try to get it going. What can be quite stressful if you're not used to this, because it is tiring. So the first steps in the project went better than I thought. So we could produce the molecule, we could select it, we made a lot of it, we could trap it, but then the water just would not stick. So we tried everything, we cooled it down to minus 270 Kelvin, we kept it at room temperature, we added a lot of pulses, we put it in like this. It was just not working. We contacted actually then some other scientists who work with similar instruments, and they said it should work, so we tried again. But at some point then, after like 3 or 4 days, we had to decide, because the first beam time, the first laser time was coming up. We had to decide, are we going to try harder and then maybe it's not working on the day, or do we try something else?
Their first beam session was in fact 5 days ago. At 5 o'clock, the beam was directed to them. But the tags don't stick. The experiment does not work.
So the orange one is the one with the mouse selection.
On the second beam day, they tried with hydroxypyrene instead of pyrene, an easier molecule for water to stick to.
under the aluminium foil where the powder is in. You heat the sample into a gas phase and allow this gas phase molecule to go inside the source.
But it still didn't work. To decide what to do with their third beam time, they hold a Zoom conference. It's with Professor Joplin, who has returned to Toulouse.
Oui. See also some 217 and some 218, but we couldn't tag them. So maybe we can go to 150 on the oven. I don't know. What do you think?
But you have to be careful also for the experimental spectrum because...
They decide to now try a new tag.
To see how much of ions we can trap.
So this evening, for their third session, they're going to try with neon tags.
And then in the next days, we'll see how it goes. Huh?
It's good that we had a plan B to go forward. Otherwise, we lose the opportunity.
It never runs as you wish, as you put in the proposal. It's always, you have to always adapt. And the more scientists we are, the more we can think about the problem.
We saw that we can produce it.
Yeah.
So I guess this one will be, let's say, easier for today.
Yeah. Yeah.
We hope so. Being here and observing how things happening is really interesting for I think every PhD student to see how things can go fast and how much you should be able to adapt with this situation.
In FELIX, it's a bit different than in other big instruments because the shifts are 8 hours, so you need to be extremely fresh for the shift. But then you have 1 day of switch off, let's say, of trying new stuff on the machine, and then again a shift.
Tell me about your need for students to think about plan A, or maybe plan B, or maybe plan C, or maybe plan D.
Yeah, that's a saying we have in our group also. Motivated with this, so we also have to, I have students in my group, so we also have to apply for beam time. And I always tell them, and also the users, that if the plan A is the main focus, but you should think about what I then call plan B, or C, D, E, as you said, is what would be the next best thing. So if A doesn't work for this reason, what could we do to still answer the scientific questions you might have, even if it's diverting a little bit.
So this evening, for their third session, they're going to try with neon tags.
What do we have here is the reservoir, and then you have the valve where you open and you allow the vapor to go into the other parts of the source. We saw the reduce in the number of
The experiment worked, the measurements were good, and they have recorded the spectra they wanted.
Here, the number of counts come again because they didn't absorb the light. And also here, on the right, yeah, you can get the infrared spectra of the mass that you are measuring.
So we have done some very nice measurements now. So that is so there's some nice results, and now we have the last of our beam times tomorrow. So now we feel confident that we now can go back and try what we tried in the first place again, but now with a lot more knowledge on what we can expect. And hopefully, so I cross fingers that tomorrow we will see what we want to see.
In fact, the last session was great. Shouts of joy and relief when the water messengers did their job and stuck. So what came out of this short-term mission to FELIX? They have 2 good detailed infrared spectra for hydroxypyrene, one by tagging with water and one by tagging with neon. Both have not been measured before. It's a richer result than they had planned for. The differences between these spectra are going to make interesting further work.
Quick scan.
I was a PhD student, that the most important thing you learn is to higher your frustration level when you do a PhD.
Tell me about Sandra. I mean, I noticed that she was in your experimental area for hours with you, taking her supper in the kitchen and so on. Tell me about her involvement with your work.
What I've learned from Sandra is really to adapt for the situation whenever problem happens, and to also, it's good to communicate in a good level for a user to understand really better what they want to do. So
it sounds as though the involvement, cooperating, getting to know scientists here must be a very important part of what the students take home with them.
That is my great hope, that it really gives them a lot of insight. I mean, it's you come here into a different environment. You see a lot of things just happening, a lot of instruments, so you can just learn by looking at that. But I think what is more important is that you are really involved in the experiments we do here. So of course I don't expect any of the students of the ESRs coming here to after one day run the experiments by themselves, but I do expect them to be involved, to take parts on it, to really be in the lead sometimes when we have to make decisions. So sometimes the supervisors might not even like this, but if I know that this is a PhD project of someone, I like to ask the students directly what they would do, what they would think in discussions. And nobody, I mean, it's always a teamwork, so nobody is alone in a project. But I find it very important to enable them that they can actually make the decision of the next step in the project.
What will you tell your friends and colleagues and other students when you get back to Toulouse?
What I will tell them is I will tell them about the let's say not the disadvantage, but more is like the problem solution. Don't expect to go somewhere and get what you want as easy as like that. It's not just because you have a proposal, you made it that it is gonna work in your brain that it is gonna work. It's not. It's a pain. So you have to come, you have to work on it, you have to test it, you have to put in your mind all the unexpected things that can happen. I would tell them about all these ups and downs with the real story, let's say.
So what have I learned through coming here to FELIX? What could be useful to you? All short-term scientific missions are going to be so different, it's not useful to generalize. But if you think about what happened here, I'm sure that would be a good preparation for yours.